Okay, do you know what is a superconductor?
Uh, kind of, but not really. Like we haven't got into that yet.
Oh, okay. Then never mind. Let me quickly introduce you. Um, Normally a superconductor is something that has zero resistance when the temperature is low enough. Are you okay?
Yeah. Okay.
So for example, let's say this is resistance, this is temperature. It behaves something like this. Like the higher the temperature, the greater the resistance. But suddenly, at a certain temperature, suddenly your resistance simply drops to zero. Are you fine?
Yeah.
So
Okay.
this temperature is known as critical temperature. And you know what? Normally the critical temperature is a very cold, all right? It's a very low temperature. If one day you are able to discover that there are some materials which can have zero resistance when the temperature is like it's like normal temperature and room temperature, that means we have basically hit the jackpot. All right.
Mm.
So the problem now is we know there is some superconductor. And then the good news of superconductor is that it has no resistance at all. When it has no resistance at all, the current can simply flow forever.
Yeah.
But the bad news is normally the critical temperature that we have found so far is something which is really, really cold. If you want to make the temperature very cold, it actually costs some money. All right.
Yeah.
Okay. And you know that for okay, so whenever you do mechanics, right, normally we say something like, okay, please ignore air resistance, please ignore frictional force with the ground, please ignore whatever.
Yeah.
This is exactly the case for superconductor because normally a conductor will have some resistance, but for superconductor, the resistance is simply zero. Okay.
Okay.
So you can have. Oh, by the way, let me ask you, what is the coldest temperature ever? Like,
Coldest temperature.
uh, like for example, is there something like lowest temperature ever, and then is there something like highest temperature ever? Is there an upper limit or a lower limit for temperature?
Not really, no. But I
Mhm.
mean, to what it can reach, probably not. But to what we've got to, probably. Like,
Theoretically, the lowest temperature we can ever go is 0 Kelvin, which is negative 273.15 degrees Celsius. Okay, theoretically, this is the lowest temperature ever, meaning that we cannot get colder than that. All right. And then for the highest temperature, we have no limit. You can go as high as possible. Are you fine?
yeah.
I repeat, for temperature, we only have a lower limit. We don't have an upper bound for the temperature. Are you fine?
Yeah. Okay.
Okay, so now you can have a look at the first page and then you can ask me any question if you want to. Or if you want to move on, then you can just tell me, then we can move on to the next page.
Yeah, I think the first page is fine.
Okay. Have you ever heard of electromotive force and internal resistance, by the way?
Yeah. Yeah.
Okay. So let me ask you a question. So now, let's say I go to supermarket, I go to a supermarket. Now I bought what? I bought a battery. Okay. So I
Mm.
was supposed to connect it with a larger resistance. And then I've got a switch here. So I'm going to put some dot here. Did you know what is the purpose of having the dotted line here?
The dotted line? No. but
The dotted line meaning that everything within the dotted line is a battery. Are you fine?
yeah,
So this represents EMF, electromotive force, and this represents the small letter R, which is the internal resistance. Are you okay?
yeah,
And now I'm going to tell you that we are now connecting a voltmeter here. Did you know that a voltmeter should always be connected in parallel?
yeah.
Okay, so let's say this is the battery that I bought from supermarket just now. And then when I read the label, they told me that the battery can offer me 2.4 volt. So I'm going to use a voltmeter to detect it. And now, I really get 2.4 volt. But
Mm,
now I'm going to do something. I want to turn on the switch here. Are you okay?
yeah.
Meaning that the 2.4 volt is the reading that I obtain when the switch is open. But now I close the switch. Do you think will there be any changes to the voltmeter reading? Will it increase, decrease, or stay constant?
It should be decreased, no?
Yes, it should be decreasing. So now if I have connected the switch, then let's say it drops to 2.2 volt. Are you happy?
No, but
Are you okay? So this is exactly what happened here. So now the thing is 2.4 volt is actually the electromotive force, which is the biggest potential difference ever of a battery.
mm,
And when I open the switch just now, this is what happened when I open the switch, isn't it? When I open the switch just now, okay, when I open the switch just now, is there any current passing through?
no, there's no current.
Mm-mm. And let me ask you a question. Do you think the current is going to passing through the voltmeter?
Uh, no,
Yeah, no, this won't happen. Did you know why?
because voltmeter has insanely high resistance.
Yes, an ideal voltmeter has like infinite resistance, and an ideal ammeter should have like zero resistance. Are you okay?
Yeah.
And then just now, when there is no current passing through, that means the internal resistance cannot steal away any potential difference. All right.
Mm,
So that's why just now there is no loss voltage due to the internal resistance when the switch is open. Are you good?
yeah, that
But
makes
now,
sense.
if I close the switch, there will be some current passing through, and then the internal resistance is going to take out some loss voltage. Are you good?
Yeah,
And let me tell you, the internal resistance is like a bad guy. It has no useful purpose at all. Are you fine?
yeah.
I mean, internal resistance is like a good for nothing. Internal resistance is totally useless. Okay.
Mm-hmm.
But what about the capital R? The external resistance, the capital R. Sometimes it's useful. All right. For example, if I want to use water heater, if I want to use, let's say, hair dryer, I really need the capital R to be a very high resistance so that it can dissipate more heat energy, all right? So that it can heat out the water, all right?
Yeah.
Mm-hmm. Okay, so let's come back here. So have you learned something? Have you learned something like this? Like, let's say this is V, right? And then let's say this is the current. So V, capital V equal to capital I times capital R. And then you have the E equal to V plus IR. So have you seen this equation before?
Yeah, I have.
Okay, so do you have any question that you want to ask me?
I remember reading through notes and they're talking about something about lost voltage. Is lost voltage just the voltage that internal resistance takes away?
Yes, the loss voltage is referring to the voltage taken away by the internal resistance.
Ah, okay.
And
Fine.
like what we agree just now, we agree that the internal resistance is like a good for nothing. Internal
Yeah.
resistance has no useful purpose at all. All right. So that's why we are going to call that loss voltage. Are you fine?
Yep.
So the loss voltage is exactly the one that I have circled with green color. All right.
Yeah.
And you know that mathematically EMF should be larger than the voltmeter reading. Are you good?
Yeah.
Okay. Now you can have a look. Oh, by the way, did you know or did you remember the definition of electromotive force?
Uh, there was no straight cut definition, but I'm pretty sure it's the voltage when the voltmeter is connected in parallel to a circuit with an open switch or something like that, when there's no internal resistance.
Oh, the one that we talked about just now is like a method. It's like a method for us to measure
Mm.
the EMF and the potential difference. But that's not the definition. Are you good?
Yeah,
Just
sorry.
like
Okay, because that's the
no.
definition the school gave me, so that's probably why.
Oh, okay. EMF is like the work done by the okay, that's the work done to bring. Hang on, let me write down the entire sentence first. So the definition of electromotive force should be something like work done. The work done per unit positive charge to bring it throughout the entire circuit. Are you okay?
Yeah.
And then the definition of potential difference is the work done to bring a unit positive charge from a point to another point in the circuit. So you can imagine EMF is like the work done to bring the unit charge to go through the entire loop, to go through the entire circuit. But then potential difference is just the work done to bring you from a point, from a location to a certain location in that circuit. Are you fine?
Yeah.
Okay.
Okay.
That is the definition. So your definition should have something like work done. Are you fine?
Yeah, work done. Okay.
The one that you mentioned, something like when you open the switch or you close the switch, that is just a method that I tried to tell you regarding like how we are going to measure this in the lab. But that
All
is not
right.
the definition. Just like if I ask you what is the definition of force, are you going to tell me F equal to ma? Are you going to do that?
No.
No, we are not going to say that. We are not going to say that. Oh, fine. Oh, definition of force. Okay, fine. F equal to ma. No, we are not going to do that. Instead, we are going to tell people that force is the rate of change of momentum. Because it was from here, the force being equal to the rate of change of momentum, that we are able to derive the Newton's second law, the F equal to ma. All right?
Yeah.
Okay, does it make sense?
Yeah, makes sense.
Okay. If I zoom out like this, will the handwriting, will the writing be too small for you, or is it still okay?
No, I can still see just fine.
Okay. So now I have a little task for you. Out of the four possible points here, you are required to get me three of them, and you know that this is a package, so you need to choose one. Okay, so can I give you like maybe 10 seconds? You have a look and you can ask me if you have any questions, all right?
All right. No problem.
Okay, are you still okay about that?
Yeah, good.
Can we move on, or maybe you need some more time?
Can move on. No problem.
Okay. Okay, so now let's talk about the total internal reflection of light. Are you okay?
Yeah, okay.
Okay, for this one, maybe I need to open a document here. Give me a second. So have you basically learned about total internal reflection before?
Yeah, we touched on it a little bit.
So today I have a little experiment here where I'm holding a laser point in my hand and I'm going to shoot the laser into a semicircular glass block. Are you okay?
Yeah.
So
Okay.
now in the first case, by the way, did you know that this stands for normal line and L, normal line? Are you okay?
Yeah, it's fine.
And the normal line should be perpendicular to the boundary. Are you fine?
Yeah,
Okay.
makes
So
sense.
the reason why I have the normal line is because I want to measure the incidence angle and the reflected angle or whatever. Are you fine?
Yeah,
Are
okay.
you going to measure the angle from here to here? Let's say from here to here. Are you going to do that?
No.
No, we're not going to do that because the angle should be measured from the normal line, not from the glass boundary. Are you fine?
Yeah.
And today, have you ever heard of critical angle there?
Yeah, I have.
Okay, fine. So now when your incident angle is smaller than critical angle, you will have refraction, meaning that the light is going to like come out from the glass and then entering the air. All right.
Mm,
And then this happens when your incident angle is less than critical angle. Are you fine?
yeah.
And so this is refraction, and we have something known as Snell's law, all right, which is something like n of the glass sine I equal to n of the air sine R. Are you happy?
Yeah.
Sometimes I prefer to call it n1 sine theta 1 equal to n2 sine theta 2. Are you happy?
Yeah.
Okay, so now let's look at another possible case. When your incident angle is just equal to critical angle, what will happen is the light will actually be traveling along the boundary. Are you fine?
Yeah.
So this is the exact case, like when when your incidence angle is exactly equal to critical angle. Are you fine?
Mm,
And
yeah.
finally, when you increase your internal angle, when you increase your incidence angle, when you increase your incident angle so that it's bigger than the critical angle, what will happen is you will have total internal reflection. Are you fine?
Yeah. It's
And
fine.
please call that total internal reflection because some student will do something like this. They will say that fine, since we call that total internal reflection, why don't we just call that reflection? No, because when you call that reflection, normally you have a mirror, like a wall for the sound to be reflected back. Are you okay?
Yeah.
Meaning that total internal reflection (TIR) is definitely not the same as reflection. All right.
All right.
And do you know that let's say the applications of total internal resistance is some total internal reflection is something like optical fibers. Did you know optical fibers?
Yeah, we just didn't go into much depth in that.
Oh, okay. Like maybe when I'm driving at night, if my car lights suddenly hit, let's say if the light is being shone onto any cat's face, then somehow I can see that the cat eyes are very bright because the cat eyes are very good at like total internal reflecting the lights towards you back. All right.
Hmm.
And like diamond, okay, we trap the light inside diamond so that the light does not escape the diamond easily. So which is why the diamond looks shiny. All right.
Mm, okay.
Mm-hmm. And one more thing is like this. This is like a periscope. All right. Let's say now we are in a submarine and then I want to see what is going on shore. So this is what I'm going to use. Are you okay?
Yeah.
Instead of Instead of having two pieces of mirror, I can actually replace the mirrors by glass prisms. Can you believe that?
Oh, yeah.
That means I have actually two pieces of glass prism. I mean the triangular glass prism today. And then I have total internal reflection occurring in the glass prisms. Are you fine?
Yeah, okay.
Okay, so far so good. Periscope.
Yeah, so far so good.
Okay, then maybe I should come back here. Oh, by the way, one more thing. Oh, one more thing. Yes. Have you seen these three formulas before? Now have a look. Because I always convince my student that normally when it comes to refractive index, well, we only have like a few formulas. Like we have a very limited number of formulas. So you can have a look and tell me whether you have seen them before. There are three equations here.
I've seen everything except for n equals c over v.
So sorry, did you say that you have seen this before or not?
Yeah, except for n equals c over v.
Okay. So reflective index of the medium is basically the speed of light in vacuum divided by speed of light in that medium.
Oh, okay. Yeah, never mind, I have.
Oh, you have heard of this?
I have just different symbols. I think it was,
Oh,
yeah, just different symbols.
so which symbols are you using?
It was something like, what was it? Let me
Maybe V
check.
over V prime?
Yeah, probably.
Okay, so I guess the symbols have very much to do with how the different books could have different symbols. Are you fine?
Yeah, makes sense.
Okay. And you know that n equal to 1 over sine c, right? If you know the refractive index, you could know the critical angle. Okay.
Okay.
I forgot to tell you, like, did you know that the higher the refractive index, the lower the speed of light in that medium?
Yeah.
Hmm.
Okay.
And could you please tell me what is the speed of light in vacuum?
In vacuum,
Hmm.
it's like um 3 times 10 to the power of, it was either mm,
3 times 10
forgot,
power 8 meter per second.
8. Okay.
Hmm. So that is the highest speed we can ever achieve. Are you okay?
Yeah.
Like
Okay.
theoretically, we cannot even be, we can't even be faster than the speed of light in vacuum. Okay?
Mm.
Just like theoretically, the lowest temperature just now should be 0 Kelvin. We can't really get colder than that. And
Mm.
we can't get faster than 3.0 times 10 power 8 meter per second. Are you fine?
Yeah.
Okay.
Okay.
And then the last one, n equal to sine n over sine r. Actually, I hate this sometimes because I prefer to call it n1 sine theta 1 equal to n2 sine theta 2. Are you fine?
Yeah, I understand. Yeah.
Because whenever we tell students about this formula, it only makes sense when one of the mediums should be air or should be free space, all right? For vacuum.
Mm.
Are you fine?
Yeah. Yeah.
Okay, and just a quick question. Can you please tell me two conditions for total internal reflection to occur?
So the material has to be more dense than air, or basically has to be more dense than the material the
Hmm.
beam is coming from. And the other thing is just the incidence angle has to be larger than the critical angle.
Okay, I like it. So your light should go from a denser medium towards the less dense medium, and then the incident angle is greater than critical angle. Fine. Okay. And yeah, you know optical fibers, right? Do I need to introduce that to you?
Yeah,
Do you take
please.
your breakfast regularly?
Yeah.
Okay, that's good. So most probably you are not going to have this problem because for people who don't have their meals, okay, who don't have their breakfast regularly, let's say you can touch wood if there's let's say a hole in their gastric or whatever, then we are going to
Mm.
use the optical fiber to see what's going on in their digestive system. All right.
Mhm.
And apart from medical use like this, like the one that I have drawn here, we also use optical fiber to like transmit a lot of data. Are you fine? On the internet.
Yeah. Hmm.
Okay, so far so good.
Yeah, so far so good.
Okay, maybe it's time I come back here. Hang on. Okay, now coming back here. So today you actually have been given the critical angle, which is 49 degree. And are you able to, wait a minute, you are now given that the speed of light in water is 2.25 times 10 power 8 meter per second. So what they want you to do is you have got to prove that the critical angle is 49 degree. Are you fine?
Yeah, okay.
So have a look at the two equations here, 2 marks.
All right.
Okay, are
Water,
you okay with this?
water to air, C over V.
And of course, you can check which symbols are you using because just now you claimed that most probably you are using different symbols. All right. I also like it if you use different symbols because the small letter C, sometimes small letter C is the speed of light in vacuum, sometimes it's the critical angle. It's quite confusing as well.
Yeah, it can, yeah. But it makes sense. It's,
Okay, can I move on?
yeah.
Okay, now have a look at this.
Mm. Okay.
Okay, so they told us that the P is at like the right middle of the pool of water, isn't it?
Mm-hmm.
So that's why this is like 3.5 meter because this is exactly at the right middle. Are you fine?
Yeah. Yeah, okay.
Okay. And did you know why that? Did you know why I need to get this angle? Well, because that's useful for the question following. Now have a look.
Yeah, that makes sense.
Okay, so we are now discussing like if the light actually enter the point K, what will happen to the light? So now, according to the geometry here, we knew that the incident angle should be 54.5 degrees, isn't it?
Yeah.
And just now in the question above, we know that the critical angle is like 48.6 degrees. So in this case today, our incident angle is greater than critical angle. So do you know what will happen?
Internal reflection.
Okay, total internal reflection will occur. So the light does not come out. All right, the light does not emerge from the what? From the water into the air.
Okay.
Okay.
Yeah.
For me, if you ask me, I like it when the student is mentioning what kind of scenario is happening now. And one more thing is we need to remind ourselves, do we really answering the question? I mean, do we really answer the question, Are we really answering the question? They ask me whether they can emerge or not. So of course we have to answer them, yes, it will emerge. Or maybe no, it won't emerge. Are you fine?
Yeah.
Okay.
Okay.
Okay. But of course, according to the mark scheme, I think they said that these two, you need to choose only one. Is that fine?
Okay.
Okay.
Yeah.
Now have a look here.
Okay, that makes sense.
Mm. Okay, so far so good.
Yeah.
So they told us that the wave is like moving. I mean, it's a dynamic wave. Are you okay? A progressive wave. Are you fine?
Yeah, yeah.
So at a certain angle, okay. Did you know that this is normal line once again?
Yeah, because it's 90
Mhm.
degrees the wave.
Okay, very good. So yeah, very good. So it is like 90 degrees to the water surface at this point. Are you fine?
Yeah.
And we definitely need to draw out the normal line because we want to show people like how do we get the incident angle, whatever. All right.
Mm-hmm.
So there will be a situation where your incident angle is like very small, smaller than the critical angle, and that is why refraction can happen. Are you fine?
Yeah, okay. That makes
So now,
sense.
now let me ask you a question. Okay, I have two questions for you. Do you think the light is going? Hang on, I have a few options for you. Your first option, the light is going here. Your second option, the line is going in a straight line. You know, like straight line with the green line just now. The third option is like coming out like this. Okay, and just for your information, this is a straight line. This is a straight line. Are you happy?
Yeah.
Okay, so today you have A, B, C. You can make your choice now, or maybe you can give me more than one answer if you want to.
I think it should be sh hmm.
Let me zoom out a bit. Maybe you need some information. I don't know.
I think probably A, no? It's obviously, it's not B, it's either A or C. Um, because the light it moves faster outside the water, so I'm just trying to think. I think it
I
should be A.
Okay, I give you 10 seconds. You have got to like fix your answer. Okay, 10 seconds.
A, I'll just go A.
A, yeah, apple. All right.
Yeah.
Okay. Unfortunately, your answer is wrong. The answer is secret. Okay,
Okay.
now let's talk about this. Just now, I appreciate when you say that B is totally impossible. Are you fine?
Yeah.
Because we know that during refraction, your angle will change unless your light is going perpendicularly to the surface, then only your direction won't change. Are you fine?
Yeah.
So that is the only exemption, like if your light enters a medium perpendicularly, meaning that when your angle of incidence is zero, then the refraction angle will also be zero. And I like it when you say that B is impossible. So let's get rid of B, okay? B, you are gone. So just now you were struggling between A and C, am I right?
Yeah.
I have something to let you know today. Like, okay, fine. So let me get rid of A, because like I told you, the answer is secant. Are you good?
Yeah.
And obviously your angle of refraction, okay, small letter r is the angle of refraction, right? Angle of refraction. Oops. Okay, so now I have something to tell you. Did you know that your light is traveling faster in the air and then slower in water?
Yeah.
Okay, let me jot it down. Your light is traveling slowly in water, and your light is traveling so fast in the air. Are you happy?
Yeah.
And I have something for you to remember today. Like if you are moving very slow, you are so close to the normal line. If you are moving very fast, you are much further. I mean, you are so far away from the normal line. Are you fine?
Yeah. Okay.
I repeat. The summary is like this. If you are moving so slow, then you are so close to the normal line. If you are moving so fast, then you'll be further away from the normal line. Is that clear?
Mhm. Yeah. Makes
So that's
sense.
why C is the answer. Are you fine?
Yeah.
Okay, then give me 1 minute. I need to go back to the notes. Okay, if people ask you what is a refraction, what is your answer? Like refraction. What is refraction? What's the phenomenon?
When it's pretty long. It's like when the waves are like not waves, the light is or waves go in at an angle from one denser to less dense or less dense to more dense at a specific angle, one part of the wavelength slows or speeds up before the other, wavefront speeds up before the other, causing the direction or angle to change, kind of.
Okay, okay, I like it when you tell me this, but actually the definition of refraction is pretty simple. We only mention that when the wave is entering a different medium, then the speed will change. Are you fine?
Yeah, okay.
But I like it when you mention something like part of the wavefront will get slowed down first, and then part of the wavefront will be like slowed down later on. Okay.
Yeah.
Okay. Now, I give you maybe 20 seconds to help me to have a look at these notes first. All right. And you need to ensure that you know that frequency does not change. Frequency does not change in refraction. Are you fine?
Yeah.
Only the speed and the wavelength are changing.
Okay.
And then I'm going to ask you, like, can you describe how does the wavelength change and how does the speed change in this scenario here, in this situation?
Just when the waves like slow down, they they slow down one at a time when they go into the different medium, so they will bunch up closer together, basically, right?
Mm-hmm. So the thing is like this, today the water wave is moving so fast in the deep water region, but the waves are moving very slow in the shallow water region. Are you fine?
Yeah.
And wait a minute, just now when I asked you to give me the definition of refraction, it seems like you are using the word light instead of the word wave.
Yeah,
Did I
wave.
hear that? Because actually, I didn't mention it was refraction of light. I mean, refraction could be for water wave, could be for sound wave, could be for light wave, and any other waves. All right.
Yeah, okay.
Okay, so now have a look at this. So from here, I purposely draw a normal line because I want to tell students how to get the incident angle and refracted angle. And basically, as you can see, the wave is moving so fast, okay, so fast in the deep water region. And then the wave is moving so slow in the shallow water region. And that's what we mentioned just now. When you are moving very fast, you are further away from the normal line. When you are moving so slow, you are so close to the normal line. Is that fine?
Yeah.
And now, when I zoom in, did you know that frequency is a constant? Like frequency is a constant when it comes to the refraction. Like your frequency is not going to change. Are you happy?
Yeah. Yeah, happy.
Can you tell me what is the definition of frequency?
Isn't it? Frequency is 1/time, no?
1/period, not 1/time.
1/period.
Because I know that you are trying to tell me this one, right? It is 1/period, not 1/time. Can you tell me what's a period then?
It's time one wave. It's was it wavelength? No. Time, one part of a wave. Oh, time it takes for one wave. Not one wave. It was
Time taken for one. I mean, you are so close, Time taken for one, I guess.
Yeah, I
One.
know. I'm trying to word it correctly. I'm
Mm.
trying to word it correctly. Time taken for a wave to pass a point, a certain point.
Time taken to complete one oscillation. Okay?
Oscillation. Okay, never
Or
mind.
time taken for one complete cycle. Time taken for one complete wave. Are you good?
Yeah.
But I think you already know the what the pattern, the time taken for one complete blah, blah, blah. All right.
Yeah.
And so
Mm.
frequency is one of the period, but unfortunately, this is not the frequency. I mean, this is not the definition of frequency. I appreciate you told me that frequency is one of the period, but actually
Yeah.
frequency is like the number of oscillations per unit time, the number of
Mm.
waves passing through a point per unit time. Are you okay?
Yeah. Yeah.
So I tried to tell you like frequency is number of waves passing through a point per time, not per
Yeah.
period, per time. Are you fine?
Yeah.
And then if there are 5 waves coming into the boundary per time, there should be also 5 waves coming out from that boundary per time. Are you fine?
Yeah.
So
Fine.
that's why the frequency won't change. That's why I have written down F1 equal to F2 here. All right.
Yeah. Okay.
Just like let's say when you go for jungle trekking, let's say you and your friend, I mean together there are 5 of you going into the jungle. I should
Mm.
expect 5 people coming out from the jungle at the end of the day, isn't it?
Yeah.
Can I say that maybe 5 people coming into the jungle and then let's say there are only 4 coming out?
No.
Or maybe there are 6 coming out?
Yeah. No.
Either one is a horror movie, right? Isn't it?
Yeah.
So that's why the frequency should be the same. Are you good?
Good.
And now can you compare the wavelength in the deep water region and the shallow water region?
Yeah. It's smaller in the shallow region.
Normally, we are not going to use the word smaller. We are going to use like shorter wavelength. Is that fine?
Okay. Yeah. Okay.
Shorter wavelength in the shallow water region and longer wavelength in the deep water region. Let me
Okay.
think. Smaller wavelength, bigger wavelength. It's weird, lah. It's weird. All right. I'm not going to say that it's wrong. It's just weird. All right.
Okay. Yeah.
And can you also compare the speed of the wave in deep water region and shallow water region, please?
Uh, it's faster in the deeper water and slower in the shallow water.
Okay. So you see, when your velocity is very high, your lambda is also very long. Are you okay?
Yeah.
Just like when you go to a shopping mall, those people with larger walking steps, they tend to walk faster. And those people with a smaller walking step, they tend to walk slower. I mean, they are taking their own sweet time in the shopping mall. Are you fine?
Yeah.
Okay. And let me think, is there anything that I have missed out? Did you know that wavefront is 90 degrees to the direction of propagation of wave? I mean, wavefront is
Yeah.
always 90 degree, and 90
Probably.
degree to the direction of propagation of wave. Are you fine?
Yeah. Okay.
Okay. Okay, so room for discussion. Do you have anything to ask me so far?
So far, no. It's good.
Okay, fine. Let me come back here. Let's have a look at this. See if you are happy with like these three marks or not.
Yeah. Good.
Okay, so far so good.
Yeah, so far so good.
Okay, let's come here. What is a monochromatic light? Monochromatic.
It's only one color.
No, we are going to reject the answer. Light of
Mm.
one single color. No, reject. Did you know why? Light of one single color, if you say that dark red and light red, they are all red in color, but they have different frequencies. They have different wavelengths. Are you fine?
Yeah.
So light of a single color is like, it's too general already. Like light red and dark red, they actually belong to the same color, which is red. But we don't do that. All right. So please don't say red. I mean light of a single color. Replace the color with the word frequency or wavelength. Is that fine?
Yeah.
Hmm. And just now, I think I have told you what is an optical fiber, right? Isn't it?
Yeah.
Okay, so the monochromatic light can travel at the same speed in the optical fiber, and then they should have the same reflective index. Because for your information, reflective index actually depends on your frequency, isn't it?
Yeah.
Like the red color and violet color will actually experience different reflective index. Are you okay?
Yeah. I'm okay.
So can you tell me what is the name of the process where a white light is entering a glass prism, and then somehow you have like some rainbow colors coming out from that prism? What is the name of that phenomenon?
I forgot the name actually, but
It starts with D, maybe D something.
the is it just called dispersion then?
Dispersion. Okay, dispersion is the process to generate the rainbow. So now have a look at this. Where is it? Oh, here. Now have a look. Dispersion of light is I mean, we can understand it like a refraction of white light, not monochromatic light, because white light has got a lot of frequencies and a lot of wavelengths. Are you okay?
Yeah.
I repeat, white light is definitely not monochromatic.
Mm-hmm.
So now, by looking at the diagram, can you tell me like which color will get slowed down more in the glass prism, and then which color is going to get slowed down less in the glass prism?
Which color will get slowed down less? Will they? Will they all not get slowed down by the same amount?
No, some of them will be slowed down even more.
Hmm. So I'm guessing from the diagram, the slowest violet bends the most, but like
Yes, yes. So now the thing is, in the air, all the colors are moving at the same speed, 3 times 10 power 8 meter per second. But in the glass, the red color will be slowed down by a bit, and the violet color will be slowed down much more. All right.
yeah.
However, when you return, I mean, when the lights are coming out from the glass prism and then entering the air again, the light will like regain the speed of the 3 times 10 power 8 meter per second in the air again. All
Yeah.
right. And normally I will ask students like, please remember that red color will bend more. Sorry, red color will bend a bit, and then violet color will bend more. All right.
Okay.
And to be honest with you, I need to tell you that these two numbers are just something that I used to bluff students. All right. I actually don't know how much to be slowed down. Not because I don't want to Google, but because I don't know what is the reflective index of the glass. Are you okay?
Yeah. Okay.
So I can only use some figures here to, to bluff you, to try to
Yeah.
convince you that red color will be slowed down by a bit, and then purple will be slowed down by a lot. All right. But what
Okay.
is the number? You have got to check yourself. All right. I don't know what is the glass anyway. All right. Okay.
Yeah.
When you learn chemistry, you know that we have so many glasses, right? Borosilicate glass. What else? Fused silicone glass. I don't know. I forgot the names already. All right.
Yeah.
Okay. Are you happy?
Yep. Makes
And
sense.
and so hopefully I have corrected your misconception that all of them will be slowed down by equal amount. No, no such thing. Okay. Life is
Okay.
not that simple. All right.
All right.
Okay. Good discussion.
All right. Okay.
Okay. Now, okay. Now have a look. So if you are using a monochromatic light in optical fibers, you can get rid of material dispersion. You can get rid of the rainbows. I don't want rainbows in optical
Yeah.
fibers.
Okay.
Mhm. Have a look. By the way, do you have any question to ask me?
No, so far it's okay.
Okay. That's great. That's great. You're not from Malaysia, right? Are you?
Yeah, actually from Malaysia, part Malaysian, part Canadian.
Sorry, part of Malaysia, part of.
My mother is Malaysian, but my dad is Canadian from Canada.
Oh, so are you now living in where? Like in Malaysia?
No, I don't live in Malaysia. I live in somewhere near Dubai in the Middle East.
Oh, okay. Nice to meet you. Nice to meet you.
Yeah,
Because I
nice to
need
meet
to tell you that I do have some students taking AQA, but not this international AQA. Are you fine?
you. Yeah.
So meaning that you are going to be my very first student in this international AQA, not the normal AQA. Are you fine?
Yeah, not many students study this
Yeah,
international.
this is quite rare. At least for me. At least for me, this is quite rare.
Yeah, it is
I
rare.
believe
It
most
is.
students are taking Cambridge A levels, by the way.
Hmm. Usually, yeah, I don't know what other people take, but yeah.
Mhm. So yeah, I need to tell you that like me, do you have the textbook of this? Like,
Yeah, I do have the textbook.
I mean the PDF version, like soft copy version.
I don't have the soft copy, but I can
Okay,
ask for it.
okay, it's fine, it's fine. And by the way, you can tell me like how can I help you? Because some students actually will like I don't know, some of them will actually list down some problems and then they maybe need my help, or some students maybe need my help to like spoon feed them from the notes or
Hmm.
whatever. So you can tell me how can I help you? All right.
Yeah, usually what I do is later into like the topic, I start doing past paper questions and stuff. And usually what I'll do is I'll go through the past paper questions. And if I read the mark scheme and find something that I can't explain myself, then I'll usually ask.
Okay, fine. That's cool. That's cool. Because actually for Saturday and Sunday, my schedule is a bit packed. So I think I can only dedicate 1 hour for you for the time being. All right.
No problem. No problem.
Okay, let's have a look at this. So how the changes are you going to make to this design so that you can reduce the dispersion? All right. So for example, you want to use a very small diameter. Okay. Just make sure that this diameter is very small. Why? You want to make it very small so that you can only take in a very small amount of light. Are you
Mm,
okay?
yeah.
If you're taking so many of lights, all of them are coming here at different angles, whatever, all the waves are dispersed already. Are you fine?
Yeah.
Or maybe
Fine.
you can use something like plastic cladding or whatever cladding if you want to. And maybe you want to use the glass of the lower reflective index, all right?
Yeah. All right.
Anyway, choose three of them. All right, just choose any three of them. Mm. Okay, can I move on?
Yeah, I can move on.
Have you learned this before? Like in the hydrogen atom, you have got so many levels.
No, I haven't learned actually.
Oh, so for your information, wait a minute. Have you learned chemistry like let's say, like energy levels? Have you heard of that before?
I have, but not in great detail, just GCSE grade.
Okay, first and foremost, I need to tell you that all the energy levels here, they have negative value to show that this is a bound system. A
Hmm.
bound system meaning that the electrons can only live in any levels here, but they cannot live from the atom. Are you okay? Unless the electron has been promoted to ionization here. Okay? Meaning
Okay.
that when you are here, that means you are finally free. If you are not there, as long as your energy has a negative value, meaning that you are bound to the atom forever, unless somehow you get some extra energy. All right.
All right.
And for your information, the lowest n you could have is actually n equal to 1. We don't start from n equal to 0. And don't ask me why. This is by default, all right?
Yeah, okay.
Okay, so let's say the electron is coming down. Book. Are you fine?
Mm.
They
Yeah.
will emit some kind of wave. Are you happy?
Yeah, okay.
And let's say the electron is falling down. Whoa, this one, oh, it falls down a greater distance, isn't it?
Mm.
Isn't it? I mean, this purple colored electron falls down a larger distance. Are you okay?
Yeah, okay.
But of course, like if you learn physics, actually you should know that electron has no color because it's like
Yeah.
smaller than the wavelength of light. So are you fine?
Yeah.
Okay. Have you ever heard of UV light, visible light, something like that
Yeah.
before?
Yeah.
Mm-mm.
UV light. Right.
Okay, for your information, as long as you are falling down to n equal to 1, you are emitting UV light. Is that fine?
Yeah.
I
Okay.
repeat, as long as you are falling down to n equal to 1, you are emitting UV light for sure. And this is for hydrogen atom. Are you okay?
Yeah, okay.
And so that means I don't care, maybe from 5 to 1, maybe from 4 to 1, from 3 to 1, I don't care. As long as you fall down to n equal to 1 level, you should be emitting UV light. Are you happy?
Yeah, okay.
And then when you are falling down to the n equal to 2, like I said, I don't care you are going from 3 to 2 or 4 to 2 or 5 to 2 or whatever to 2, you are emitting the visible light. Is that okay?
Mm. Okay.
And finally, apart from these two levels, any other transition, like all the things that I have drawn here, will give you something like infrared. Are you fine?
Okay.
Maybe I should keep this for the future because this has something to do with the Paschen series, bracket series, fund series, or whatever. Are you okay?
Yeah, all right.
Okay,
Okay.
one last question for today's class. Did you know that the sun is emitting infrared, visible light, and UV light all the time? Like, the sun is there, so it's emitting, infrared, UV, I mean, visible light and UV. Are you okay?
Yeah, okay.
And did you know that visible light is something that makes you feel like, oh my God, the sun is too bright. I can't really see that directly. Is that okay?
Yeah, yeah.
And do you feel hot under the sun?
Yeah.
So the hot, I mean the heat, is caused by what kind of radiation?
Infrared, no?
Okay, infrared. And then can you detect UV? Like, can you say that, oh my God, the ozone layer is depleting, so I can see the UV light coming down here. Can you do that?
No.
We cannot detect UV light, and that's what makes it so dangerous. Are you happy?
Yeah.
Okay, an unknown enemy is always the most dangerous enemy. All right.
All right.
Okay,
Okay.
so far so good.
Yeah, good.
Okay, so I think that's it for our class today. Any question you want to ask me? I can give you some time if you have any question to ask me, maybe.
So far it's okay. It was pretty good. I understand it now. It's more clear. Yeah.
Because sometimes I prefer if the student like I don't know. Okay. Tell you what. Maybe okay. Do you have like any materials regarding this international AQA? Like, do you mind sharing them with me? Hmm.
Yeah, I can share. I'll look through it and send. Definitely has have some
hmm.
sheets and stuff. Yeah.
Because all my worksheets, all my past year questions. Oh, by the way, I can download the past year questions from online. Like you don't have to
Mm.
share with me the past year questions for international AQA. I can download it from online. I mean, in fact, I have downloaded it.
Okay.
But I think I need the notes or whatever because for your information, the notes I used just now is actually like from the other syllabus. All right, not
Yeah.
from the international AQA because, like I said, it's not really popular here in my region.
Yeah. Same. Usually for notes, the only thing we have is textbook, and because they don't actually publish notes themselves, the exam board. So usually what I do is have to reread the AQA notes instead of international AQA. But
Oh,
I can give the textbook. I'll ask my teachers for a digital copy of the textbook and I can send it.
okay. Mm-mm. Okay, fine. Because
I
I actually cover like I teach Cambridge A level, ESL A level, AQA A level. But this
Yeah.
international AQA is my very first time. Yeah, so basically, if you ask me any physics questions, I think I should be able to answer you. All right.
Yeah. Mm.
Okay. No?
Okay.
Anything else to ask me?
So far it's fine, but maybe next week I'll have something.
Okay. Okay.
Okay.
Mm.
Thank you so much.
All right. All right. You're most welcome. So that's it for today. So see you next time. Bye bye.
See you next time. Thank you. Bye.
Most welcome. Bye bye.